Hi everyone, today we're going to be talking about binary ionic compounds. Our goals are to explain what ionic bonding is and how it occurs, determine the formula unit for a binary ionic compound, and then utilize the rules to correctly name binary ionic compounds. So quick review, ions form when atoms gain or lose electrons. Metals, which have relatively a small number of valence electrons, generally lose their valence electrons to form positively charged cations. When an atom loses electrons, that leaves more protons in the nucleus, which makes the ion that forms positively charged. Nonmetals have a relatively large number of valence electrons, and the easiest way for them to achieve an octet is to take on extra electrons. When they do that, they get a negative charge, and they're called anions. This doesn't happen in isolation. For one atom to gain electrons, another atom has to lose electrons, so it happens in tandem. Then you get oppositely charged particles, and they're going to be attracted to one another. So the ionic bond is simply that attraction between the oppositely charged particles. Particles that are oppositely charged have different electrostatic charges, and the attraction between them is an electrostatic attraction. So an ionic bond is the electrostatic attraction between oppositely charged ions. Right? So don't let that term electrostatic attraction scare you. It just means it's the attraction that particles that have different charges feel for one another. That's what an ionic bond is. And by the way, we'll talk about other kinds of bonding, metallic and covalent, and those are also electrostatic attractions. The only difference is the kind of particles that are involved. What are the positive and the negative particles? So here's a little loop, and it kind of shows the transfer of an electron from a sodium atom to a chloride ion, to a chlorine atom to form a chloride ion. When that electron is transferred, the sodium forms a sodium ion with a positive charge. The chlorine becomes a chloride ion with a negative charge, and then they're going to be attracted to one another. So it doesn't occur in isolation. We can show this using a Lewis dot symbols. So sodium, if you remember, is in group 1, has one valence electron, so it has one dot in its Lewis dot symbol. Chlorine is in group 17, and it has 7 valence electrons, so 7 dots in its Lewis dot symbol. And we can kind of easily see what's happening here. This one electron that sodium has is transferred over to the chlorine. That leaves a sodium ion with a positive charge, and then a chloride ion now has, instead of 7 valence electrons, all 8. Right? Put that in brackets to kind of hold everything in, and with a negative charge outside. So that represents sodium giving up 1 electron to chlorine, right? Formation of 2 ions, which are now strongly attracted to one another, forming an ionic bond. So the name is bond, ionic bond. Taken, not shared. Get it? Okay. Now, once we know kind of what ions are involved, it's pretty easy to write a chemical formula. The formula unit for an ionic compound just tells us the simplest ratio of ions involved in forming a neutral compound. So the example we've been talking about so far, the formula for sodium chloride is NaCl. That's the formula unit. Even though the ions themselves have a charge, the ionic compound is neutral. Those charges cancel each other out. So there's always going to be an equal number of positive and negative charges. So it cancels each other out. Now, when you look at that formula, it kind of makes you think that that sodium chloride is kind of just composed of little sodiums and chlorines attached to one another. But that's not actually the case. It's really like massive numbers of positives and negatives that sort of combine in a crystalline lattice. But we'll talk a little bit more about that in our next slideshow. So we'll hold off with that for now. Okay, now we've learned the formulas for a bunch of different monatomic ions. A monatomic ion, again, is an ion that's composed of just one kind of atom. Right? We'll learn about polyatomics in the near future as well. If we know the charges on the ions, we can write the formula unit for any ionic compounds. So if I want to write the formula unit for potassium oxide, right, I can kind of think of this as a balancing act. I have to make the number of positive charges equal the number of negative charges. So the potassium ion has a charge of +1, it's in group 1, and the oxide ion has a charge of -2. So when I put those two together, just one of each, I don't have an equal number of positives and negatives. What I need to do here is actually add in another copy of potassium, and that will give me 2 plus charges to equal my 2 minus charges, and that gives me the correct ratio of potassium ions to oxide ions. So the formula for potassium oxide is K2O. Right, when we write that formula, we don't show the charges anymore because they have canceled each other out. But what we do include is a little subscript here, and that shows us how many potassiums there are. Oxide doesn't need a subscript because we understand if there's no subscript, that just means one of those. Right? So this is what we want to be able to do with our names and formulas. So general steps, if you want to kind of have a framework. Step 1, determine the charges on your ions that are involved. Step 2, always put the positive ion first. So it's going to come first in the name if you're given the name of the compounds, but if you're just given 2 elements, whatever is positive is always going to go first. After you look at your charges, you add in extra copies of ions to make sure the positive and the negative charges are equal, and then you can write the formula using subscripts when you have more than one copy of an ion. Okay, so let's do, don't show charges. Let's do a couple more examples. So magnesium iodide. Our magnesium ion has a charge of 2 plus. Our iodide ion comes from iodine. It has a charge of 1 minus. Again, not equal, so I have to add in another copy of iodide. Okay. When I write the formula, that now gives me 2 pluses and 2 minuses, MgI2. So the little subscript shows how many iodines I put in there. I understand I only have 1 magnesium. Right? That's the formula for magnesium iodide, and cation always goes first. Charges are the same on both sides. Lithium nitride. Lithium has a charge of 1 plus. Nitride has a charge of 3 minus. So in this case, I'm short on pluses. So I'm going to add in 2 more lithiums, right, to get that to balance. And so the formula for my compound is going to be Li3N. That is the formula unit for lithium nitride. And one that's a little bit more tricky, aluminum sulfide. Aluminum has a charge of 3 plus. Sulfide ion has a charge of 2 minus. All right, so I'm a little short on negatives. 2 negatives, 3 pluses. If I put in another sulfide, now I have too many negatives. So I'm going to keep adding ions to both sides until I balance for charges. So really what I'm doing here is bringing them both up to a +6 -6, finding essentially the least common multiple, right? And the formula for aluminum sulfide is Al2S3. Got it? Okay, now what about the elements in the middle of the periodic table? Remember this? There are some elements that have more than one common charge. Well, we'll know what charge to use because the charge is part of the ion name. Iron 2 has a charge of +2. Iron 3 has a charge of +3, right? Same as the Roman numeral. Lead 4 has a charge of 4 plus. Okay, so once we figure out what the charges on the ions are, it works exactly the same way. So iron 3 chloride, that must be iron with a 3 plus charge. Chloride has a 1 minus charge, so I need 3 of those chlorides. So my formula, FeCl3. What about tin 4 oxide? Well, Sn, 4 plus for my cation. Oxide is a 2 minus, so I need 2 of those, and my formula will be SnO2. That gives me 4 pluses and 4 minuses, so it's nice and balanced. You try it. Okay. Pause. All right. And for aluminum fluoride, you should have AlF3. And for chromium 2 nitride, you should have come up with Cr3N2. Okay. Binary ionic compounds. Everything we've been talking about is a binary ionic compound. Binary just means relating to or involving 2 things. And so the 2 things here are the 2 different elements that are involved, right? Only 2 different kinds of monatomic ions. What it doesn't mean is that there's just 2 ions in the formula unit, right? You could have something like AlF3. There's 4 ions total there, but what matters is it's just aluminum. It's just fluoride. Okay. Now, naming binary compounds. All we have to do is name the cation and name the anion. Little tricky here is we have to include the Roman numeral if needed. So that's where people usually find stumbling. But if no Roman numeral is needed, then you don't have to worry about it. The other thing you have to remember is when you're naming the anion, an IDE suffix. So for example, if you wanted to name BAS, right, our cation there is the barium cation. Our anion there is the sulfide anion. And so that's just barium sulfide. Barium's in group 2. It doesn't need a Roman numeral. All the metals, so if the metals that need Roman numerals are in the middle of the table, the transition metals, and then also commonly like tin and lead. Right? We have a couple of exceptions that don't. Silver, zinc, and aluminum that don't need Roman numerals. Okay, so let's name these. None of these need Roman numerals. This is just calcium chloride. Next is aluminum oxide. And then barium bromide. Okay, now something that people want to do in this situation sometimes is they see the 2 and they think that has to be part of the name. For ionic compounds, it doesn't work that way. It's just calcium chloride. Anyone who knows their ions and their charges will know that the formula has to contain 2 chlorides, so we don't have to worry about that. Okay, now, you have to be a little bit more careful because some of those metals do require Roman numerals. So for example, chromium is in the middle of the table. It's a transition element. It can be either a 2 plus charge or a 3 plus charge. So we have to figure out which version it is so we can include the correct Roman numeral. So what we're going to do is work backwards from fluoride. Fluoride is always -1. Okay? So if I have 3 fluorides in there, that means I have 3 times -1. I have a total of 3 minus charges. And so I must have 3 plus charges too. And so that chromium, that single chromium ion there, must be carrying that 3 plus charge. And so the name of that compound is chromium. And then in parentheses, Roman numeral 3, fluoride. Okay, so it's a little tricky. You do have to be careful. Okay, try another one. What's the name of FeN? Again, start with the nitride. Nitride is always N3 minus. There's just one of them, so that's 3 minus charges. So we must have 3 plus charges. So the charge on iron must be Fe3 plus. This is iron 3 nitride. Okay, what's the name of Cu2S? Again, working backwards. This is the sulfide ion. Sulfide is 2 minus. So that's 2 minus charges. That has to be equaled by 2 plus charges. Now, in this case, there are 2 coppers. And so for 2 coppers, to make a total charge of 2 plus, both of them must have a 1 plus charge. And so that means that this is copper 1 sulfide. Okay. So the 2 is how many copies of the ion is there, not the charge on the ion. So be super careful there. Right. One more. Cr3p2 phosphide ion is a 3 minus. So our total number of minus charges is 6 minuses, and so that must be equal to 6 pluses. And so each chromium there, not Cu, sorry about that, Cr must be 2 plus. You have 3 of those. That gives 2, 4, 6 pluses, so this is chromium 2 phosphide. Okay, so what are the names of these? Pause it, give it a try. And here are the answers. Silver chloride, even though silver is in the middle of the table, it doesn't need a Roman numeral, it only makes a 1 plus charge, so that can be left out. Technically, it wouldn't be wrong to call it silver 1 chloride. Cobalt 2 fluoride, calcium oxide, iron 3 iodide, and manganese 3 sulfide. And then, can you write the formula unit? Going back to the first thing we learned. And here are your answers. ZNO, calcium bromide, is CaBr2. Tin 2 nitride is SN3N2. Gold 3 chloride, it's not on our ion list, but guess what? It has a Roman numeral, and so we know what its charge is. It's Au3+, and so our formula is AuCl3, and then magnesium sulfide. All right, so that's our binary ionic compounds, and in the near future, we'll be talking about ternary compounds and also the properties of ionics. All right, so see you later.